Okay, we're going to talk about a very important concept, and that's chemical equilibrium. Okay, or we just say equilibrium. Now, when we talk about equilibrium, it's a dynamic equilibrium. In other words, once you hit a static point, it doesn't mean everything stops. What it just means is that all the changes are constant. Okay, so we talked about equilibrium in the context of vapor pressure. Remember, we had this being in a vacuum, and then we let it reach equilibrium, where the number of molecules that go into the gas state is equal to the number of molecules that go back into the liquid state. And at that point, we measured the pressure, and that was vapor pressure. And we said that going back and forth, that's a dynamic equilibrium. Okay? So, in general, what we're saying is this. If I have a reaction here, AA plus BB, very general reaction, goes to CC plus DB. All we're saying is that the reaction rate forward, this way, is equal to the reaction rate in reverse. Now, does that mean that I'm going to always form 1 mole of C with 1 mole of A? No, that's not what we're saying. We're saying that how fast this goes forward is going to be equal to the same amount it goes backwards. If I start a reaction and I don't have any product, I'm not at equilibrium. Okay? So just so you know, this is a special case where reaction rate forward is equal to reaction rate in reverse. So, when we write this out, the reaction rate forward, okay, so I'm going to say this is a constant. This is called the rate constant. So the reaction rate forward is going to be equal to my rate constant, okay, times A times B. I'm going to use these, okay? Now, the reaction rate in reverse looks like this. Instead of these being products, if I'm going in reverse in this way, these are my reactants. So I'm going to say K in reverse. That's R. Okay, that's KR. All right. And this is going to go to these guys, all right? And the reaction rate is equal to K R C C D D. Okay? So why is this important? So we'll just do a little bit of math here. And we're saying that they are equal. So what we're saying here is that at equilibrium, okay, then the rate forward is equal to the rate in reverse. Okay, and I'm just going to manipulate the equation here. What I'm going to do is I'm going to keep this here. I'm going to divide both sides by KR. And both sides by A to the A, B to the B. That's a constant. We said that was a rate constant. That's a constant. So we'll just call it K a constant. And this is actually called my equilibrium constant. So what's crucial here is this. When you look at an equilibrium reaction, first thing you have to determine is, when we're doing this, you have to say, am I at equilibrium? Okay. What affects it? Your K can be affected by temperature. Okay. So we always, it's not in the equation, but whenever we write down a reaction, we specify the temperature. The other thing is this. If you're not at equilibrium, then we'll talk about how we handle the situation. Okay, so the first thing is, whenever we give you concentrations to try to calculate K, you have to make sure, are these equilibrium concentrations? Okay, and so let's go ahead and take a look at this concept of equilibrium. So if we look at a reaction, let's take okay. Okay. And let's say, I believe you're running this at 25 degrees Celsius. Okay. All right. So how do we do this? This is colorless. So when we start off, we don't see anything. We start seeing the development of a brown haze. This is basically what makes it smog. All right. Okay, so this is time. And what you're going to see is this. If I start off, this is my concentration. If I start off with just dinitro tetroxide, over time it gets consumed in its reaction. If I have no nitrogen dioxide, over time, as I consume this, I start forming my nitrogen dioxide. At some point in time, though, the proportion, the ratio okay, of the concentration of nitrogen dioxide to my nitrogen tetroxide becomes a constant. Okay, so it looks like with my graph, it's right around at this point in time. I reach equilibrium. Some reactions will reach equilibrium really quickly, and in other reactions it takes some time. But in either case, over time, basically you're going to see that this reaction will reach equilibrium. Now let's just give you a different example then. What happens if I started off instead with my nitrogen dioxide. Then over time, some of it's going to be consumed, okay? And if I didn't have any dinitrogen tetroxide, it'll get consumed until at some point in time, the ratio of nitrogen dioxide and dinitrogen tetroxide becomes a constant. And that ratio is the same. If it's always at 25 degrees, that ratio here is going to be exactly the same as the ratio that we were talking about from the previous graph. And in fact, what happens if I start off with some let's say I started off with a mix, some dinitrogen tetroxide and some nitrogen dioxide. Okay? Again, at some point in time, I will end up getting the same ratio. And at this point, that's what we mean when we say that we reached equilibrium. So in summary here, before we continue on, is that regardless of where you start, when you reach equilibrium, at equilibrium, the ratio of the concentration of your products divided by the concentration of your reactants will be the same regardless of how much material you started with in terms of reactants and products. Okay, you'll always go to the same equilibrium. Same temperature, same reaction. Okay, so that's the idea behind chemical equilibrium. Okay, and as you can see, when we did the calculations, it's products over reactants. Okay, so basically the bottom line is that when you say, how do you calculate your equilibrium constant? The first thing you should be thinking is products over reactants.